So the purpose of IARPC is to foster interagency coordination on research related to the Federal Arctic Research Plan. This is enabled through a network of teams. So the focus of the modeling team, or the Modelers Community of Practice, as it's known, is to enhance understanding of the Arctic system through the use of regional and global Earth system models. The modeling team co-leads are myself, Wilbert Wire, and Renu Joseph. We are joined today by the atmospheric team and their co-leads, Heis de Boer and Barry Leffer. The current 5-year Arctic research plan was implemented in 2022. To address the new plan's focus on deliverables and to build on our ongoing approach of reporting research activities in our meetings, Renu, Wilbert, and I discussed a series of meetings that would focus on enduring deficiencies and issues with Arctic modeling. So we propose that in a limited time, we have a frank discussion about where things stand, what could be concluded, what approaches could be pursued, and modeling community needs for observations and other resources in order to move the needle on difficult issues. This is our second meeting in this format. We are focusing today on the modeling representation of Arctic clouds and their effects on the surface energy budget. Generally, we may think of difficulties associated with Arctic cloud representations over a sea ice surface. However, we're not limiting ourselves to that. We can discuss cloud issues over high latitude land surfaces and glaciers as well. The Arctic climate is an integrated system, so we may need to discuss a series of interconnected modeling topics in order to access source issues with cloud modeling, surface representation, large-scale circulation, moisture availability from lower latitudes, etc. This meeting is also occurring in a real-world setting, so we have practical time limitations. We may have technical issues, etc., but we would like to see what can be accomplished. And we very much would like to thank everyone for their participation today. And now Hazel will start us off with a Mentimeter question for our audience.
Okay, great. Thanks, Richard. So as I mentioned, we're going to do a brief audience poll before we get started. And the idea here is just to give you all a chance to engage and get you thinking and participating in the meeting. So there are 3 different ways to access the poll. One, if you're on your computer, I'm going to place a link in the chat. Whoops. There you go. So you can click that link and it will open in your browser. If you'd like to use your phone, you can scan the QR code, or on your phone or your computer, you can go to menti.com and enter the code that's shown here, 17241653. Again, that code is 17241653. And I see we have folks in joining here, and I'm going to go ahead and join from my phone as well so I can follow along in case there are any technical issues. As you join, the screen will be fairly blank, just instructions and the thumbs up, and I see folks are hitting that thumbs up, and so I can see folks coming in. I'm going to go ahead and jump to the next screen. You can, again, continue to join from that link or from going to menti.com and entering the number at the top of the screen. This is just a welcome slide. And the first question that we have for you all today is, in your opinion, our current representation of Arctic clouds in climate models is, and the options range from excellent to laughable, or if you don't know, that's okay too. Seeing a clustering around so-so. Apparently no one thinks they're excellent. And this is great. We'll give folks 1 more minute to enter. Nice. Okay, we have 1 person going out and saying they're good. And yeah, again, a big peak around so-so. It looks like there's certainly room for improvement. We'll go ahead and jump to the next slide. And if you didn't answer that question, you'll see a bar at the top of your screen that will say go to slide. And that'll just skip to where we are in the poll. This next question is, as compared to CMIP 6, I expect uncertainty in Arctic cloud processes to be reduced in CMIP 7. And true or false? And we are seeing a really even, first few answers were really even. folks who took a breath to think about it seem to be clustering around false, but we'll see. Okay. Maybe we'll hear from our panelists later for some other opinions here. But it looks like there's not a true consensus, but a bit more folks thinking that this is false. And I believe those are our first two questions. And we're now going to jump to presentations. We are going to come back to Mentimeter a little later in the session, so feel free to keep it open and just turn back to your Zoom screen. Thanks so much.
So now we're going to have our presentations. So we'll have two expert presentations on the topic of modeling clouds in the Arctic. The first one is going to be given by Tristan LeCrae from the University of Wisconsin. Tristan, hello.
Okay, hello, thank you. Let me share my screen here. Zoom that. Okay, see if I can minimize the pictures on the side. Okay. Yeah, thank you for inviting me to give this talk. So the goal of my presentation is, well, I guess twofold. One, I would say, illustrate kind of one way that we can use some satellite observations to try to understand the answers to this question of how well do we model Arctic clouds. And then in doing that, basically, I'm going to try to show what I feel is probably the state of the art in our knowledge of how well we actually do model clouds in the Arctic. I'm going to start with actually a couple of motivating slides that are a little bit more relevant to the second point that you brought up, which is Arctic energy balance. And I think this will lead into a discussion of why it's important to understand how well we're modeling clouds. And I know several of my co-authors, actually, I should point out my co-authors, Ann Sled, Ellen McElhatton, Hamish Prince, and Cameron Bertosa. They're all students or former students of mine. And I know a few of them are on the call now. And there'll be other results that I'll show from others that are also on the call. But this is some recent work that Ann Sled did with me a few years ago, where we were just looking at trends in the amount of absorption, the amount of solar radiation the Arctic is absorbing. And on the right-hand side, or sorry, on the left-hand side of the plot, you see what we would expect as sea ice reduces. The Arctic Ocean is absorbing considerably more shortwave radiation, even within the last 20 years. This is the series time period than it did at the start of the century. On the left-hand side, what you see is the picture when you include clouds. So this is the all sky scene, or the clear plus cloudy sky scene. And what you see is we do still see a trend where the Arctic is absorbing more shortwave radiation, but you see that the trend almost everywhere is reduced relative to clear skies. And so this is just, showing the potentially obvious feature that clouds reduce the amount of shortwave radiation that arrives at the surface. But it's important to note that the reduction is very significant. It actually reduces the trend in the amount of shortwave radiation that the Arctic is absorbing by a factor of 2 relative to clear skies. Now, I want to take this a little step further. This is work that a new student of mine, Hamish Prince, has recently submitted to the Journal of Climate, where we took a same look at not only the trend in shortwave radiation being absorbed, but at the amount of outgoing longwave radiation that's being emitted from the Arctic atmosphere. And so the panel on the top here shows essentially the same result you just saw, but now expressed as an Arctic average. The gray line there represents the clear sky absorption. You can see the very strong increase in absorbed shortwave radiation. And the black line represents what you get when you look at the all sky conditions. So again, this factor of 2 reduction relative to clear skies. On the lower panel, though, what you see is the outgoing longwave radiation. You see that it's also increasing. But hopefully you can also tell that the change in the slope in going from the gray clear sky curve to the black all sky curve is significantly less. The effect of clouds is significantly less than it is on the outgoing longwave radiation than it is on the absorbed shortwave radiation. In fact, it's 5 times less. And so the result of this is actually when you look at all sky conditions and you add these two things together and look at what the net Arctic energy imbalance is doing, there's actually no trend in the last 20 years in the net Arctic energy imbalance. And a lot of this is due to the fact that clouds are reducing the amount of extra shortwave radiation that the Arctic is absorbing. So another thing that we did then was to sort of take that result and say, okay, how well do climate models reproduce this reduced uptake of shortwave radiation in the Arctic due to reduced sea ice? And so one way that you can do that is you can look at the time to emergence of those trends in all sky and clear sky Arctic shortwave absorption. And what I'm showing here, this is a consolidation of a lot of analysis that Ann Sled did again, where we're actually looking at just the ratio of how quickly does an all sky trend in shortwave radiation emerge relative to a clear sky trend in shortwave radiation. And what you would expect is if the clear sky is increasing at a faster rate, you would expect that all the clouds would slow it down, and it would take longer for a trend to emerge in the all sky conditions relative to clear sky. So you would expect this ratio to be greater than 1. What you find from CERES, if you look at the plus sign there, is that the ratio is about 1.25, as I showed on the previous slides. And what we saw when we looked at CMIP5 models is that most CMIP5 models also capture that same cloud masking. That the vast majority, with the exception of maybe one model, show that the rate of emergence of all sky trends is slower than clear sky trends. But interestingly, at least we found, in CMIP6, about half of the models have now reversed this opinion, and they actually suggest that the all sky trend in absorbed shortwave radiation is faster, actually emerges more quickly than the clear sky trend. And if you could trace kind of where this comes from, it actually looks like it is because the all sky trend in absorbed shortwave radiation itself is actually stronger than the trend in clear sky. So that's a fairly strange result, and it points to, you know, potentially something I don't know, that's changed in perhaps not a good way in going from CMIP5 to CMIP6. I'll also point out in this diagram that if you look at where the plus side resides on the x-axis, what we're looking at here on the x-axis, which I didn't even mention already, is the sensitivity of top of the atmosphere albedo to changes in sea ice. And what you see is that CERES actually lies to the right of the vast majority of all of the models in CMIP5 and CMIP6. So it suggests that the top of the atmosphere albedo in the climate models is not as sensitive to sea ice changes as it is in the observations. Just another point to make there. Okay, so like I said, all of this leads to the question that we're asking today, which is how well do models actually represent Arctic clouds? And I want to show a series of results here. This is not an exhaustive list by any means, but these are results from some people that have done a lot of good work on understanding this problem. What we're looking at on the left-hand side here is some older results, but still very valid, from Greg Cezanna, who I think is on the call, who looked at the Calypso LiDAR GeoCCP product and compared that with the LMDZ model in France. This is work I think Greg might have done as a PhD student. And you can see, so what we're looking at here is a height, day of the, or month of the year cross-section of liquid cloud occurrence on the left and ice cloud occurrence on the right. And I'm not going to go into the details here of what the results are showing. The main point is that there are some very important differences in the way the model captures clouds versus the way the observations are suggesting cloud cover varies. One of which is that there's a liquid cloud observed at much higher altitudes at all times of year than there are observed at higher altitudes than the model actually predicts. But you can also see that the model produces too much ice, especially in the colder months, the winter months, at lower elevations, especially than is observed. On the right-hand side, we have some results from GenK, which does something similar, but using the CAM5 model. Now we're looking at just total cloud fraction that comes out of a Calypso simulator. On the top, you have the results from the Calypso LiDAR itself, and on the bottom, you have the results from CAM5. And what we can see, especially in the wintertime, is that there's this significant underestimate of cloud cover in the model relative to the observations. That does exist. It persists, let's say, over the Greenland continent in the summertime as well. But the summertime clouds over the ice and the ocean look a little bit better than they do in the wintertime. So we already have some evidence here from some of these previous studies that there are indeed some model biases in the cloud and the representation of clouds. This is another result from Patrick Taylor looking at the CMIP5 ensemble. Those were just two individual models. This is now the whole ensemble from CMIP5. And here the comparison is against C3M, which is the CloudSat Calypso series MODIS radiation product. And so this is also using the active sensor observations in the Arctic. The black curves here represent what the C3M observations and the ERA interim and MERA 2 reanalyses show, whereas all the colored lines here represent the various climate models. And again, without going into detail, I just want to point out that both the actual annual cycle itself, the minimums and maximum in the annual cycle, as well as the magnitude of the cloud fraction are widely varying between the various climate models, and very few of them really agree with observations. On the right-hand side, they actually further break down the comparison into low cloud and high cloud. And you see that a lot of the variation, especially in the phasing of the annual cycle, actually comes from the representation of low clouds. And so again, there's this kind of hint that it might be related to the phase of clouds or ice microphysics that's causing some of these biases. One last comparison, because this is going to lead into a point that I want to make about some of the satellite observations. This is some work from Ariel Morrison, who was working with Jen Kay, and maybe Greg Cesana as well as co-authors. What she was looking at in this particular figure was just the frequency of what's called opaque clouds from the Calypso LiDAR perspective. I want to point this out because this is a very robust metric from observations. Basically, we're just looking at what profiles does Calypso not see a return from the surface, meaning that the cloud is so opaque that the LiDAR doesn't penetrate through the cloud. And on the upper row here, you can actually see the frequency of occurrence of these opaque clouds coming from the GeoCCP simulator in CES-M1. And in the lower panel, you can actually see the bias relative to observations. And once again, you can see, especially in September, October, and November, there's a significant bias where the CES-M1 model did not capture the frequency of these opaque clouds, which are probably related to a lack of cloud liquid in some of these clouds relative to the observations. So again, this is where I want to just emphasize this point. One of the reasons that we haven't known a lot about the way Arctic clouds are represented in climate models until fairly recently, the last decade or so, is because these active sensor observations are so critical for doing this. This is an example, just a single swath from CloudSat and Calypso going over the Greenland ice sheet. And I just want to highlight the fact that these active observations are really one of the few few ways that we have of identifying clouds and precipitation that are independent of the surface. So they provide this very robust measure of where clouds exist. And also by combining the sensitivities of the two instruments, the LiDAR being very sensitive to liquid water and the radar being very sensitive to ice, we can actually also partition the phase of the clouds very accurately. And this has kind of revolutionized our understanding of where clouds exist in the Arctic and what they're made of in the Arctic. And so that's what's led to a lot of the results that I just showed. I want to highlight one more advantage of having the radar and LiDAR together, and that is understanding a little bit maybe what the relevant processes are that give rise to some of these biases. So I'm just going to start here with this work by Christoph van Tricht in 2016, where he used the Calypso LiDAR and CloudSat radar to look at what the frequency of clouds, and in particular, the frequency of clouds that contain liquid water, were over the Greenland ice sheet. And what you're seeing here is that on average, about 40% of the clouds over the Greenland ice sheet contain supercooled liquid water on the annual average. That number is about 70% in the summer, and even in the cold winter months is still 25%. And so what this study actually did was, again, connecting back to this question about surface radiation balance, it went further and actually showed that clouds enhance the surface radiation on the ice sheet by an average of about 30 watts per square meter. And half of that enhancement, which obviously contributes to the melting of the ice sheet, half of that actually came from supercooled liquid droplets. So it's obviously very important that you capture the number of clouds over the ice sheet, as well as what they're made of, whether or not they have liquid present. And it turns out in this study by Ellen McElhatton the following year that the CESM-1 model did not have very many liquid clouds. It's sort of an understatement. They had almost no liquid-containing clouds over the Greenland ice sheet. And so this is a comparison of the A-train frequency of supercooled liquid clouds versus on the very left versus the CESM in the middle, and you can see the difference there, that big significant negative bias in the amount of supercooled liquid clouds in CESM on the right hand panel of the three vertical panels there. And so there's some indication that that is obviously going to have an impact on the downwelling long wave radiation. And maybe there's some connection between that and the fact that that CESM model also predicted ice sheet temperatures that were too cool in the summertime. But again, to come back to the processes that might be responsible for this, by adding CloudSat to the mix, we were actually able to take a closer look at the frequency of supercooled liquid-containing clouds that actually produce snowfall. And what we found was a very strong bias here, where the observations show that only about 20% of supercooled liquid-containing clouds actually produce snow, whereas the model actually liked to produce snow in about 70% of those cases where there was supercooled liquid in the cloud. And so there's some indication here that one of the reasons that the model might be wrong in terms of the, or might be missing all the supercooled water over the ice sheet, is the fact that it was producing snow a little bit too regularly. It was glaciating the clouds and scavenging up a lot of that liquid water. And maybe Andrew will be talking about that a little bit in his talk, I don't know. So I want to leave on a little bit of a positive note. Since CESM-1, what we've, I think a lot through the efforts of Andrew and company, we've actually seen that CESM-2 is doing a much better job of capturing liquid-containing clouds throughout the Arctic and over Greenland. So this is a follow-on study by Ellen McElhatton that's showing now the frequency of supercooled liquid-containing clouds throughout the year in CESM-2 in the blue curve, versus the old CESM-1 results that I just was looking at in the red curves. And what you can see is that the new model actually agrees much better with observations, which are in black. And what that's done is led to an improvement in both the downwelling long wave radiation at the surface by increasing it due to the extra liquid in the atmosphere. And it's also led to a reduction in the downwelling shortwave radiation at the surface, which is exactly what you would expect, more shortwave being reflected to space than there was in CESM-1. So this is, I think, a really nice example of some improvements that you can actually diagnose using these observations. Okay, I want to end on just a couple of notes, a couple of comments here. I basically want to reiterate the fact that these active sensor observations are very valuable. This is some work back on a previous version of the MODIS cloud algorithm. I don't know how things have changed since then, but I'm imagining some of these errors still exist. Basically, what this is showing, if you just look at the solid red and blue curves here, what you're looking at is essentially the accuracy or the hit rate of the MODIS cloud algorithm, a cloud detection algorithm with respect to Calypso over open water surfaces in red and over ice surfaces in blue. And what you can see is that there's a pretty strong sensitivity here in the accuracy of the algorithm, the ability of the algorithm to detect clouds that depends on the surface type. And so if we're looking at an Arctic that's changing rapidly and ice is being reduced, you can actually see that this passive algorithm might actually have biases in the impact of that on cloud cover, just simply due to the fact that it's more sensitive to clouds over open water as it is over ice. And so this isn't to say that we can't use passive observations, but it's much more challenging to use passive observations in the Arctic than it is active observations. And I wanted to point out that the CloudSat and Calypso era of observations is basically now over. The analysis, of course, will continue into the future. We do have EarthCare that's scheduled to launch sometime in the coming year, which is great. That hopefully will extend the record for a few more years. And then hopefully after that, we'll have the atmosphere observing system that will continue to make radar and LiDAR observations. But there's been some recent descopes to both the LiDAR and the radar that are kind of threatening whether or not we'll be able to continue to collect this really valuable, in my opinion anyway, data record for evaluating Arctic clouds. And so just a couple of other final thoughts then to kind of summarize everything. Hopefully I've demonstrated that we do have some satellite data sets that are really valuable for answering this question about cloud biases in models. And they do seem to reveal both climate models and reanalyses have some issues with representing clouds. Despite these examples, in my opinion, Arctic clouds are understudied compared to things like mid-latitude and tropical cloud regimes like stratocumulus clouds and convection. In part, that was probably due to the challenge of observing polar clouds, but we do have observations now. I think we should do more analysis. And then finally, I just want to emphasize again, it's really important to use these robust diagnostics and make sure that we don't use products that are potentially susceptible to biases due to surface type. And then hopefully try to maintain this active sensor record beyond EarthCare so that we can actually start looking at trends in cloudiness and, try to understand how not only the representation of current day clouds are, but the projections of cloud changes in the future might be in climate models. So thank you.
Thanks very much, Tristan. That excellent introduction. So our next speaker is Andrew Gettleman. For this meeting, we're employing Andrew twice. He's also representing CAM6 on our discussion panel, but he'll also be giving an introductory talk today. The title of his talk is How Not to Simulate Arctic Clouds. Andrew, welcome.
Thank you. Hopefully you can see those slides.
Yes, that's fine.
Okay, great. Thanks, Tristan, for that tremendous presentation. That was great. I learned some things even about our own models. We can talk about that later. So that's a great sort of segue because I'm going to try to provide not specific results of biases, but sort of a process level view of kind of how we do this and how we get to these clouds that we're not very good at simulating. I was not the person that thought they were good. I actually thought they were sort of so-so, mostly because in our current modeling, we're doing a lot better than we used to. Motivation doesn't really, I think most people on this call or we've already heard it, but this is a figure I like from Hugh Morrison. I'll show a picture from Ariel Morrison, no relation later, but this basically shows sort of different states of the surface long wave radiation in the Arctic and as a function of surface pressure. And you can see there's sort of two modes of this joint histogram labeled A and B. And if you look at the evolution of time series of these fields, you see these basically trajectories that kind of go from one to the other. And one is a cloudy state and one is a clear state. So as Tristan said, the clouds matter a whole lot for the surface energy balance of the Arctic. When we're talking about the processes that maintain these clouds, just to be explicit, as Tristan was talking about, why models come up with biases, and I'll get to some of the mechanics of this at the end and what I think we need to do. But there's a lot of things going on. You've got sort of most of these clouds, as Tristan highlighted, we're dealing a lot with low clouds in particular. These are trapped below the boundary layer. There's often an inversion. The boundary layer can be coupled or decoupled to the surface. That's the environment of the cloud. So you have this turbulent environment. You have interactions and coupling with the surface. Within that, it helps dictate, as Tristan said, what the cloud phase is, and how that is maintained is not just a function of the thermodynamics of the environment and the turbulence, but you also get into the phase is also dependent on what's going to glaciate the cloud. So that depends on ice nucleation and it even depends on the transport of aerosols. And so this presence in these colder than freezing temperatures, whether you have supercooled liquid or whether you actually have ice is very important. And you typically are getting these supercooled liquid clouds, as Tristan said, that actually start precipitating ice through this process. Just to show some examples, and the ones I happen to have were stuff that we've done actually in the Southern Ocean. Oh, it's just 2000, it should say 2020. This wasn't that old. On the right, you can see what's essentially a time series of a research flight out of Tasmania heading down into the Southern Ocean. And the different colors you can see here on the top represent different kinds of cloud. So on the top is actual data along this black trajectory. The black trajectory is going in and out these low clouds. The green indicates the model thinks they're supercooled liquid, and it shows the actual condensed water contents versus the observations. And you can see the crosses on the upper part are observations, and the circles are actually the model. The model does actually not a bad job of reproducing the sort of qualitative and quantitative aspects of this, except there does tend to be, if you can see this, not quite enough ice in many of these cases, or no ice. You can see sort of at the end of this flight where the model's actually producing all supercooled liquid and really no ice. And if you look on the right, this is, I should mention this is CESM2, so we're sort of getting the cloud phase right. But if you look at the medium ice water content in panel C here on the left, on the upper right corner panel C, you can see we're actually, the observations are the blue and the model is the orange. We're just not getting enough. Some of that may be, there's issues with the cloud condensation nuclei. The liquid water path is actually a little bit high. And you can see that in this panel E, but a lot of it is we're just not getting enough ice still. And that, again, ice nucleation is hard, and also these secondary ice processes are highly uncertain, and they may get involved at these temperatures with some of the cloud physics. So diving into this ice nucleation, and this is a nice recent paper by Christina McCluskey. Two things going on the left. This is, again, a Southern Ocean environment, but the high latitude aerosol environment is pretty complex. In particular, if you look at sort of the slightly larger particles, residuals, basically this sort of one on the bottom on the left, what you can see is that line AC and BC is above cloud or below cloud for the sampling. And below the cloud, it's an environment that's pretty much oceanic in this case. Above the cloud, there's all kinds of stuff going on. And the crustal stuff, this is the remote Southern Ocean. You're several thousand kilometers from the nearest piece of land. So it's actually a very interesting and different environment, which makes it hard to simulate things. Unfortunately, on the right, what you see is what we would call good agreement for ice nucleation. So this is a predicted on the vertical axis and observed from the Marcus experiment, which was on a ship in the Southern Ocean, looking at the ice nucleating particles. And what you can see is this is called good agreement, which means you're within a factor of 10. And there's actually an interesting tension in the community about how we actually represent ice nucleation. This plot in particular is an empirical, is actually been added to models as an empirical parameterization. And there are some more, what we would call physically based parameterizations with classical nucleation theory. But with our large scale models, those are actually very difficult to implement, largely because of the timescales and having to get the budgeting correct. So there's this interesting tension going on, I think, right now in the modeling community about how to represent ice nucleation, and a whole lot of uncertainty. As I said, turbulence matters. So this is from Matt Shoup's recent overview of the Mosaic case in the Arctic, and it shows the evolution of a cloud layer. And it's very nice. It shows the layer, it shows the inversion, and you can see the humidity is high in the boundary layer. And then you can actually see the evolution of wind speed and the turbulence, particularly below cloud, how that turbulence evolves in the cloud layer. And then the particle sizes and number concentrations, and some estimate of the radiation. But the tricky part is actually, particularly in large scale models, is not just getting these vertical profiles, but trying to get the coupling of the turbulence right. I'll get into that in a minute. Again, the clouds and the surface. This is from paper by Ariel Morrison and Jen Kay and collaborators at CU. And the surface matters for clouds and vice versa. We talked about that a little bit. What Ariel found is it's really in the fall when there's this tighter coupling. This shows over the fall season with an intermittent mask there. Within the intermittent mask, there's very big differences in the cloud fraction over open water and over sea ice, and the stability is very different. So there's sort of this complex interplay, and it's not necessarily just the clouds driving the radiation or creating issues in the radiation. It's a coupling between the surface and the radiation and the clouds themselves that we have to get. So what do models do? Well, all we have to do is simulate this, right? Simplified picture. central to this is supercooled water, and then you have all these sort of turbulent processes on the right, also adding the aerosols. And then on the left, you can actually, again, start to get into the cloud microphysics over here on the left. And it's really these process interactions that are somewhat difficult. Key aspects of this, in my humble opinion, as I've indicated, are the supercooled liquid and ice formation and ice nucleation, getting the turbulence and entrainment right, particularly with large-scale models that are having to parameterize that heavily, and then coupling in the microphysics and the turbulence. These are usually separate in the models, and that actually creates lots of problems. So this is what a large-scale model does, and I picked the older version of CESM. This is basically the model that's in CESM 1, some versions of CESM 1. And what you see is I've talked a lot about these different pieces, but the boundary layer and the shallow convection, and to some extent the deep convection, are all estimates of the turbulence, and more sophisticated models are actually trying to combine those things into one consistent parameterization. And of course, when you get to much smaller scales, like a large eddy simulation, those actually are sort of explicitly permitted or resolved. And then that feeds into macrophysics, is basically taking the clouds and condensate. It's sort of a cloud fraction representation. That all goes into microphysics, and microphysics can be either simple bulk microphysics. It can actually have a prognostic representation of the drop in crystal number, or it can actually be bin type schemes or hybrids between those. In large scale models, we typically don't go to particle-based microphysics, but those take in information from an aerosol scheme, either prescribed, simplified, or more detailed for ice nucleating particles, INP and CCN, and they produce distributions of condensate mass and number concentrations and a cloud fraction in a large-scale model that represents a cloud fraction. That all goes into a radiation scheme, which affects the dynamics, and then you sort of loop on this again. So there's a lot of complexities in here, and again, just like in the previous slide, it's this coupling, I think, that gets us into a lot of trouble. The microphysics, if driven correctly, can be fairly well described. The ice nuclei and the aerosols in particular are not that certain. And then the coupling to turbulence, I think, is a big problem, because we have limited ways that we actually can just take subgrid information from the turbulence and bring them into the clouds. So where are we? Well, I think in turbulence, for example, we either do it explicitly with sort of a large eddy simulation, but in anything with a larger scale than that, from a mesoscale model up through a global model, we're parameterizing the turbulence. What's happening now for large scale models is we're getting these higher order closure schemes, combining turbulence with the boundary layer and cloud formation in a consistent way. That can be good. It can also be problematic, because you now have a very complicated representation that has to then interact with cloud microphysics. And so typically these higher order closure schemes only treat liquid, because we don't know how to provide a closure on ice explicitly, or from analytically, we do the closure on ice with supersaturation representations and ice processes, which include secondary ice and liquid ice interactions. In some of these environments, GROPL may be necessary in the Arctic to get this mixed phase, but it may only matter for deeper clouds, although we started to play with that. And the types of microphysical schemes can determine the sort of bulk versus bin, can actually determine the flexibility, or particularly the bulk versus the moment-based schemes determine the level of flexibility and consistency in this. As I said, I think these turbulence microphysical actions are critical. And then activation and supersaturation and nucleation, in order to get ice supersaturation, and I think as Tristan said, one of the big advances that a couple of the models have pushed into, those using sort of particularly two-mode microphysics, have been able to actually provide a better representation of ice supersaturation by not having it as a fixed function of temperature. And that means we get a better representation of this environment. We get more ice, but we're maybe not getting it enough. And then whether we're using an empirical version of the ice nucleation, which is traditional, which is dependent on temperature, maybe it depends on aerosols, or classical nucleation theory is another aspect of this. And then that brings us into having this all dependent on aerosols, and particularly the aerosol budgets, making sure we do the scavenging and evolution of the aerosols correctly, which in the Arctic is sort of a long-range transport problem. And so that actually is also pretty difficult. You also have the aging of aerosols when you get into that. So what would really improve Arctic clouds? better aerosol budgets, I just mentioned. I think constraining ice nucleation in the mix phase. I think getting better interaction and feedbacks between the turbulence and the microphysics, cloud formation for both ice and liquid. And then that would get us into the surface coupling. How to get at these issues? Well, my favorite way to look at this, having spent a long time building GCMs for large scale models with just looking at single column model cases, and then trying to evaluate those with more detailed models and observations or using large eddy simulations as sort of truth, is that hasn't, it served us well so far. And the satellite evaluations have served us well, but to get at the processes, I think we need to use sort of a hierarchical modeling approach where we're trying to put the same complexities, the same interactions and representations, same parameterization suites together across scales to compare to the detailed observations like Mosaic to try to get these interactions nailed down and to get different representations and different types of representations working together. And this also has to be done in a coupled context. You can't just do with the atmosphere. The ice and the ocean are also involved in this. Last slide, I'm going to do a plug for Wilbert and Hailong's HILAT project, which is one attempt to actually do this. This is there's a great movie, but I wasn't sure whether that was going to work in here, so I just pulled a still of this. This is actually doing sort of a hierarchical modeling. It's a general circulation model, so it's the sort of E3SM based on, it's very similar to CESM, and it's got a refined mesh, so it's 100 kilometers outside of that, and it's refining, I think it's down to 14 kilometers or so, maybe it's 7. I think Hailong or Wilbert can correct me on that. But it's coupled. So as you can see, there's a representation of a storm, which is also looking at altering the ocean temperature in the Arctic environment and show how these things all interact. There's some efforts to now do this and constrain it with observations and sort of look at the Mosaic period, for example, and really try to get at that. So I think this is a way forward. I think we have a lot of these issues. I think we made some progress. But I think at the process level, we're starting to understand where a lot of these sensitivities are, even if we don't have the answers. And that's, I think, going to lead us to where we can get more data on this. And I'll stop there. Thank you.
Thanks very much, Andrew. Those were 2 great presentations for the introduction, and we're on time. So we'll next go to another round of Mentimeter questions with Hazel.
Sounds good, thanks. Let me pull this up. And we had a few new folks joining, so I'll just put the instructions to join quickly on the screen here and drop the link in the chat again. So you can use the QR code or go to the link in the chat is probably the easiest way. And I see it looks like folks are in there. If you had it open already, you can just, again, hit that go to slide button at the top of your screen. And we have a few more questions for the audience to participate in. The format of this next question allows you to rank your answers using the drop-down menu. So the question is, according to your understanding, which factors are most responsible for biases in the representation of Arctic clouds in Earth system models? So there's 7 different options there: moisture transport, aerosols, surface properties, liquid microphysics, ice nucleation, and my personal favorite, lack of puppy-related content in Earth system models. Your answers are anonymous, and this is just a fun way to get a bit of involvement. So you don't need the perfect answer, just what comes up off the top of your head. It looks like folks are getting it, but the way that you do this is you select on the drop down, and then you can drag and drop, and when you're ready, hit submit. And nice, it looks like ice nucleation and aerosols are close to the top. Ice microphysics are jumping up ahead. Give folks another few seconds to answer, and the next question will be a write-in option. So if you think there are things missing from this list, keep that in your mind, and we'll give you a chance to add those. Nice, we're getting some bouncing around. Looks like ice nucleation and ice microphysics are sticking towards the top, with aerosols coming in third. Great. And unfortunately for me, lack of puppy-related content is not high on the list. So we'll go ahead and jump forward. This was the only problem I could solve. So I went ahead and threw it in here. This is my dog who likes to join Zoom meetings sometimes, and my sister's dog who likes to look out the window and considers herself a cat, I think. Okay, we'll keep it moving. Were there any important processes missing from the previous list? And again, if you didn't answer that previous question, you can just hit the go to slide button at the top. And nice, turbulence. Yeah, I heard that in the last talk, so that makes sense that that's coming up. Turbulence and entrainment, boundary layer parameterization, cloud dynamics. Surface turbulent fluxes, liquid and ice optics. Nice. Cloud dissipation, more votes for turbulence. Okay. Precipitation related losses and aerosols, and feel free to keep entering these. I'm going to go ahead and, oh, look, we're getting a couple more. Heat transportation, circulation patterns, natural variability, aerosol nucleation, cloud dynamics, cloud regime transition. Great, these are all great answers, and I will download these results and add them to our IARPC collaborations page as well, so you can look through them again. We have one more question, same format as the last one. What actions would be most impactful to help improve the representation of Arctic clouds in Earth system models? And I apologize for the typo in that title. First vote is improving aerosol parameterizations. Give folks a minute. I know the ranking takes a moment to do. Including improving cloud parameterizations, aerosol parameterizations, and observing networks are the top 3. Communications between observationalists and modelers getting a bump right now. Surface parameterization and increasing model resolution towards the bottom of the list. Give folks one more moment, and again, we'll have an option to write in other answers after this. And I will go ahead and jump to that so we can keep moving with the panel discussion. Feel free to keep answering these questions. And again, I will upload the final results to the IARPC collaboration site. And anything that was missing from that list, go ahead and add it in here. Coupled modeling at high resolution, aerosol observations in particular, coordinated hierarchy of model studies, ocean modeling, better investment in active satellite observations, enhanced observing of mixed phase processes across scales, interaction between parameterizations, such as turbulence, microphysics to aerosols, model intercomparisons, increase the vertical resolution, more satellite observations, more active satellite observations, investment in tools to compare model outputs with observations. This is a great list. Feel free to, again, keep adding information here, and I think we'll probably hear some more on these topics in the panel discussion. So I will pass it off to Gijs, and thanks again for participating, and it's great to get some audience involvement and to have an active group participating in this call.
Awesome. Thank you, Hazel, and thank you everybody for participating in those in answering those questions. It's great to get some input to see how out of tune with reality my own thoughts are. It's wonderful to see everybody's contributions to that. So we're transitioning to a panel discussion, and there were a couple of questions for Tristan, I believe, in the Q&A, and I don't know if we want to pause for a second to answer those now. Hazel, Wilbert, others, what do you think? Or should we move on? I know we're running short on time, maybe a little bit.
I think we're okay for some questions.
Okay. It's only two, so hopefully they'll be relatively quick. Tristan, both I think came up during your presentation. One was from Ralph Kahn, who is asking about uncertainty with respect to measurements, particularly related to cloud phase. I don't know if you have any specific comments on that.
Yeah. Well, there are a few studies, I guess, that have, that sort of take a look at this. I think it's actually difficult to do from both the surface and from satellite. But I guess, I resort to the fact that the active sensors are probably providing the best estimates that we have right now. And the fact that the models are so different than observations that I think we can be relatively sure that we're not just simply looking at a observational uncertainty, manifesting itself in an observation model comparison. But I think that it's an important point, and I think especially at lower levels, like below about a kilometer or so, some of the satellite observations tend to have difficulty in detecting cloud and especially discriminating phase. Whereas I think if you look, the inverse is true from the ground. When you go up above about 3 kilometers or something like that, ground-based observations have challenges in that regard too. So it's an important point, but I think the model deficiencies are still a little bit larger than the uncertainty. That would be my opinion.
Great. Thank you. And then the second question actually came from me by way of Wilbert, and that was whether the reduced sensitivity, if I understood it correctly, you were saying there was reduced sensitivity in the CMIP models with respect to top of atmosphere response to sea ice changes. Is that the result of cloud properties, or is that potentially the result of misrepresentation of surface albedos?
Yeah, I actually think it's the latter. In fact, I don't know how it could be explained by the cloud results we saw. So I think it's almost opposite to what you would expect if it was clouds. So I think it's probably related to surface albedo, and I think there has been some studies that have looked at surface albedo as well, maybe by Patrick Taylor in the Ceres group, that have shown maybe that I know there's definitely spread in surface albedo across models, and maybe also that the model ensemble mean is a little bit biased. But that's what I would guess, is that maybe the albedo is a little bit low in the models.
Yeah, very good. Well, great. Thank you for taking the time to answer those questions. At this point, we're going to transition to our panel discussion, and we have a great group of panelists with us who span a variety of different modeling tools and kind of modeling regimes within the kind of world of Arctic cloud simulation. So we've asked each of the panelists to put together a couple of slides just to give a quick introduction to themselves and the tools and models that they represent. So Hazel, are you able to share those introduction slides? Very, very good. And I guess we have about 20 minutes for these introductions. So to the panelists, I encourage you to stay focused and to the point, but at the same time, give the group a little bit of flavor on who it is you're representing here and what your role is. So we'll start with Andrew, and Andrew, please go ahead.
Okay. I'm actually, even though I guess I was on the list for CESM2 and CAM 6, which I've spent a lot of time working on, now transitioning to do a bunch more work on E3SM, which basically comes from CESM. And what I'm showing is some examples along the lines of more detail from what I just showed with that little still, which is the 25-kilometer Arctic refined mesh. I think that's one way to get at it. And then the more extreme version of that is at the top. Those are actually, that image is actually a 3-kilometer global model. That's the advanced version of E3SM called SCREAM or EAMXX. Those are just different versions of it. And if you look on the left where it says SCREAM and Himawari up at the northern hemisphere, that's actually a cold air outbreak off of Asia. So those are mixed phase cloud streets that are evolving in the model. And I think that's a great way to compare to observations. And there are active ways to compare to observations in here. And again, that's sort of 50 hours into a simulation. These are very expensive, but you can also refine them like the one on the bottom, and then they're not quite as expensive. And this is being done for the Mosaic period right now with a number of models, including both CESM and E3SM.
Excellent. Thank you, Andrew. And next we'll move to Hailong Wang.
Hi, everyone. My name is Hailong Wang. I'm an atmospheric scientist at the Pacific Northwest National Lab. I'm here on this panel to represent the DOE E3SM atmosphere model, also known as EAM, on this discussion topic of Arctic cloud bias. In case you don't know yet, the E3SM project PI is Dave Bader at Livermore National Lab, and chief scientist is Ruby Liang at PNNL, and the atmosphere group lead is Shaochen Xie at Livermore. So all the E3SM project leadership team are in a meeting this week. So I was asked to be their delegate here. So I do wish to appreciate discussions with Shaochen and his Livermore crew, names listed here, and as well as the HiLab RASM project team on this topic. Next, please. Next slide, please. Yeah, so I just used one slide to summarize the configurations and the capabilities developed in E3SM that also helped improve simulations of the Arctic clouds and climate. The EAM model has been designed to simulate atmospheric processes and climate across scales, as Andrew already mentioned that the model has two standard horizontal resolution at 100 kilometer and 25 kilometer. It also has several configurations of regionally refined mesh, including the one Andrew showed, the mesh over the Arctic was developed for the HiLab RASM project. And also the SCREAM, the cloud resolving version called SCREAM at 3.25 kilometer resolution, which is developed for the next generation of EAM, also called EAM XX, written in C++ to be used on GPUs. So during the model development from version 0 branched from CESM, then version 1 released in 2018. Now we're currently working on version 3. We had developed new cloud microphysics schemes, convection trigger, parameterization, calibration that have reduced biases in Arctic cloud phase, especially ice clouds and the overall cloud radiative effect. I myself have been mostly being involved in improving aerosol processes and aerosol cloud interactions that reduce the Arctic aerosol low bias. Has been a long-standing problem in many climate models, and including development of explicit aerosol tagging for source attribution. Last on the list, but not the least, is the E3SM team also put great efforts in implementing diagnostic tools that can correctly and effectively combine observational multiple source observational data for model evaluation, including the satellite simulator package COSP and ground-based simulators called EMC2 that are designed for model observation comparison across scales. So my last slide next is for just more information about E3SM model and the DOE program with hyperlinks on it. If you're interested, please feel free to explore more. Thank you.
Thank you, Hailong. Next, we move to Xiaoli.
Yeah, hi everyone. I'm Xiaoli. I'm currently a postdoc at Princeton University and GFDL. So I'm representing the GFDL CM4, but only for the part of the work that I've been involving mostly during the past 1 year. So we have a small group, mostly me with my other three hosts at GFDL, Michi, who is a CS expertise, Zhihong Tan, focuses more on the boundary layer parameterization, and Neil Donor in clouds and convection, aerosol cloud interaction. So for this topic, Arctic clouds, and we are particularly interested in the surface atmosphere interactions, and more specifically, we're very specifically interested in the frozen sea ice and the low cloud interactions, and especially for those that are not resolved in GCMs. So one example here is those small scale processes that are happening over the CS openings or cracks or CSDs. And over the past almost 30 decades, and a lot of studies, most based on observations and LEAs, and they have demonstrated the importance of the CS need, mainly in terms of their efficient at transporting heat energy or moisture energy, and also they have a potential to affect the boundary layer clouds. But a few studies are really more focusing on this in the coarse resolution GCM, so that leaves a question mark here, but that doesn't mean we have made any progress over the years. For example, here I'm saying since the first RT-LEAD experiment and a few or pioneer studies using the older generations of GCM, they have demonstrated that the needs are actually quite important for the Arctic, for example, near surface temperature or the CS state. So those studies have successfully introduced a prognostic need error fraction in GCMs and replaced the fixed and constant values that are being previously used for many years. So this are the only information we have so far, and we're still using it. But I'm arguing here is that might be not enough for the Arctic clouds. So I'm showing here on top, right, is a recent work we're working on. So those are the low cloud cover monthly mean. And as demonstrated in the previous talks, like most GCMs, the GFDL CM4 in red has overestimated the low cloud cover throughout the year compared to the OPS, which is the Calypso GOCCP. But what we're doing here is we introduce the need versus not introduce the need, and we actually find something quite interesting. And those low cloud bios in CM4 are mostly introduced by the need, we argued, especially during the non-summer season, in winter and transition seasons. So I guess the key message I want to convey here is that low clouds are quite sensitive in the modeled needs, at least in GFDL CM4, and maybe we need to treat them more accurately if we want to get the clouds correct. Yeah.
Thank you, Xia. Next panelist is Lisa Bengtson. Oh, I'm sorry. Did you have a second slide, Xia?
No, that's just a backup. Thanks.
Okay, great. Lisa, please go ahead.
Okay. Yeah, I'm representing the Unified Forecast System, UFS, and just a little bit of background about myself. I'm a model developer from Sweden, and just because our country is partly in the Arctic Circle, we have a lot of interest in representation of clouds and mixed phase clouds, build up on ice build up on infrastructure and so on. So that's where my interest in representation of mixed phase clouds started for weather forecasting. Since 2017, I've been at NOAA, OER, SRL, and PSL. And I'm currently co-leading the NOAA UFS Research to Operations project. We work together with the National Weather Service on transition of physics research innovations into the UFS operational targets. So the UFS is not a model on its own, it's an infrastructure, and it can be configured into different applications. So we have a set of operational NOAA operational targets under the UFS. One is a CONUS atmospheric only regional application called RUFUS or RFS. We also have a hurricane application, which is a regional coupled ocean atmosphere system. And it also serves the GFS and the GEFS, which is the global, and under UFS going to be fully coupled ocean ice and wave atmosphere, and potentially also aerosol. And we're working towards a seasonal forecast system. So unlike the other model centers represented here, the UFS is not used for climate simulations, but goes out from high resolution I guess short range weather applications to the seasonal forecasts. If you go to the next slide, Heis. Here's just an example of the interest we have in the topic of Arctic clouds from a UFS perspective. In in this study, we took advantage of the work carried out in the Polar Cortex framework, which was a large international modern comparison study for Arctic clouds in the summer. And we added some GFS simulation to the model data, and without going into any details, the conclusion was that the GFS kind of ended up with a group of models that tend to underestimate supercooled liquid clouds and overestimate ice, which is a common bias we see in our models. Since this study, we have moved from the GFS that was just an atmosphere component with a different version of microphysics. So now we have the GFS moved to couple MOM 6, size 6, Waywatch 3, and FV3, and moved to the Thomson microphysics scheme. So we're continuing doing some evaluation with this new configuration of the GFS, and also take advantage of the Mosaic field campaign with similar studies. Sorry about that. So yeah, that's all I had.
Fantastic. Thank you, Lisa. Next to Greg Cusano.
Hi, so I'm Greg Cusano. I'm an associate research scientist at Columbia University and NASA GIS, and I represent the NASA GIS group, the cloud group. And I have I put down some names here, so you're probably familiar with most of them. And so my own research interest is basically to help improve understanding of the cloud processes and the cloud climate interaction with using some tools based on observation and climate models, and with the hope that it will reduce uncertainties in climate projections. And so, like I said, I specialize in climate model evaluation using CMIP models, and also more specifically the NASA GIS model and the latest version, especially model E3. I focus on cloud feedbacks and mixed phase clouds, also low cloud a little bit, at mid-lat and polar in the polar latitudes. And I've been doing a lot of development of climate model-oriented satellite datasets, and I thank Tristan for showing some of my results. And here is just a little more of my result with this plot of Calypso GeoCCP liquid phase observation over the Arctic. And then I use that in combination with satellite simulator, which I've been developing also to evaluate the climate models. And I didn't bring any specific results here, but if I had a message, that would be, we have to be very careful when we evaluate those models using the satellite observation. We want to be able to compare apple to apple, and so using a satellite simulator is a very good idea to do so. And I'm glad I've seen a lot of results using satellite simulators, which is good practice, I think, and I'm glad to see that. A couple of words about the team in general, and not only me. So we have a lot of focus on the mixed phase clouds, and for that we use funding from NASA at the global scale, and also at the subrate scale we want to use DOE funding and NASA funding with ground-based measurements and the field campaigns in combination with the LES to set up some specific case studies, and then use the SCM approach to try to evaluate and improve the cloud parameterization and microphysics in the model. And my goal for the session is to find out what the most pressing issues are, and how, as seen by the community, and how I can contribute to solve them. That's it.
Thank you very much, Greg. Next is Donovan Barahona.
Hello, so I'm Donovan Barahona. I'm a model developer at the NASA Global Modeling and Assimilation Office. And well, my main interest in working, we work mostly with the GEOS5 model, actually. So I'm interested in finding the sources of ice nucleating particles and mechanisms of ice formation in Arctic clouds and in general in the atmosphere, and also how to represent these complex dynamics and microphysics in mixed phase clouds. There is a typo there, and especially in these large scale models, not at very high resolution, but mostly at the resolutions typical of a GCM, like 25 to 100 kilometers. And that, of course, puts us in trying to represent the role of subgrid scale variability, which is crucial for the GCM representation of mixed phase clouds. So here I'm showing some recent work that we have been doing with IVTAN. In the top plot, you can see this is a very well-known paper by Morrison et al. Nature Geosciences. And well, it shows this liquid layer on top of ice. Sorry, that is so hard to represent in climate models. And what we found in this particular work that I think is interesting is that the ice nucleation representation is quite important to reproduce these super cool layers. And here I'm showing different sensitivity analysis that we did with using different parameterizations of ice nucleation. And what we found is that if ice nucleation is confined only to the liquid phase and it's only it's below certain value, then you start seeing this layer at the top around 400 millibars with high liquid cloud, with high supercooled liquid. So this shows us that it's very important supercooled liquid to reproduce this structure of the ice of the Arctic clouds with liquid on the top and ice at the bottom. Ivy also, actually, she went on and wrote a paper on how this may affect Arctic amplification factors and show that it could be up to 30 to 40% of the uncertainty in Arctic amplification factor can be reproduced just by ice nucleation. Thank you.
Thank you very much, Donovan. I think next is Keith Hines.
Hi, I'm Keith Hines. I'm a former research scientist, now a remote researcher at the Byrd Polar and Climate Research Center. I'm part of Dave Brumich's polar meteorology group there, which is at Ohio State. And we distribute the polar optimized version of the weather research and forecasting model. Now, more recently, I've been working on Antarctic clouds, but with WRF, we have interest in both the Arctic and Antarctic. Now, if you look at the panel on the right-hand side, what that shows is cloud forcing from the ASCOS study, which was a field program that took place near the North Pole during August and September of 2008. And 4 stages were identified during ASCOS. 2 of them, stage 2 and stage 4, were very pristine. And it was found that those pristine conditions seem to limit the production of liquid water clouds. And it was found that the number of liquid particle droplets, the concentrations were very small. And when we've done simulations with Polar WRF to look at that, when we changed the specified liquid cloud number that was in the Morrison microphysics, it definitely had an effect in terms of reducing the amount of liquid, and to change the cloud forcing and show it shows the importance, at least on the liquid side, to the presence of CCN in the clouds. Now, on the opposite side of the Earth, next slide, please. Yeah, this is this is from the AWARE study, which was done in the Antarctic. This one shows the vertical profiles from McMurdo, Antarctica, and it shows the liquid cloud fraction for a case from March 2016. Now, this study, we looked at what we called frigid supercooled clouds. These are unusually cold supercooled clouds where at least from a distance, it seems strange that liquid water was present at such cold clouds, say with -25°C or colder. And the question, of course, is why didn't the Bergeron process glaciate the clouds? Why was liquid water present? And well, observations over the southern hemisphere do show that ice nucleating particles are actually quite rare, often say an order of 1,000 less than many typical cloud parameterizations account for. And we got a new formula from Ethan Vignon, that gave a low value for the ice nucleating particles as a function of temperature, and that with my own little experiment also. And when we changed the cloud microphysics and we accounted for these very pristine conditions, in this case for the ice particles in the profiles, we found that the amount of liquid cloud fraction, also the amount of liquid cloud water as well, was very sensitive to the specification of ice nucleating particles. And so what we find, again, is that the clouds in our regional simulations are very sensitive, to the specifications accounting for the liquid and ice forming aerosols. And so we're hoping to demonstrate by these slides that getting aerosol variability, both for ice and liquid, is very important for improving our simulations of polar clouds. Thanks.
Thank you, Keith. Yeah, a lot of connections to the themes asked during the Mentimeter questions, I think. Last but certainly not least, our final introduction to panelists here is given by Amy Solomon. Amy, go ahead, please.
Okay, so hello, everyone. I'm a scientist at CERES, University of Colorado, in the NOAA Physical Sciences Laboratory, and I'm here to represent the CAPS team at PSL. CAPS stands for the Coupled Arctic Forecast System. It was adapted from the RASM, the Regional Arctic System model, for weather scale forecasting. And so we adapted RASM by changing the resolution. We run the model at 10 kilometers for all components. We've reduced the domain size, so it's just the Arctic Ocean and the surrounding land. We've changed the way the model is initialized, and among other things. And we originally developed this model for process studies, but we quickly found that the forecasts from this model were needed to support the National Weather Service and observational campaigns. So starting in 2015, we supported the ONR Seastate campaign, and we've been supporting campaigns since then, and we're going to be supporting the NASA ARC-6 campaign, which will be happening next year. And an interesting focus of this campaign will be to observe the thin clouds that the satellites cannot see. So we'll be forecasting the thin clouds with CAPS and seeing to what extent the satellites are able to see these thin clouds and to what extent we can improve at a later date the parameterizations used in the satellite algorithms. The National Weather Service uses these forecasts for guidance for sea ice forecasts. And our interests in this topic are twofold. The first is that we do research to advance process understanding of Arctic mixed phase clouds and to forecast, create products that support the National Weather Service and observational campaigns. And I have a few slides here to illustrate some of the studies that we're currently involved with. So if you go to the next slide, please, Heis. This is from a recent study using the MOSAIC observations over the wintertime period, so from October 2019 to March 2020. And on the left, these are showing the liquid water path in the upper figure and the ice water path in the lower figure from observations. This is a Shoup-Turner product. Compared to 7 state-of-the-art forecast systems. And the black and the gray shading is showing the observations. So this is in bins. And you can see on the upper figure, only one of the models is able to simulate the maintenance of liquid in clouds at cold temperatures. And that's the CAPS model. And all of the other models are completely underestimating the amount of liquid in the clouds. And all of the models are underestimating the ice as well, except for one of the models. And on the right, this is a diagnostic that we put together to look at this from a surface energy balance perspective. So what this is showing is sensible heat flux on the y-axis, conductive ground flux on the x-axis, and the colors are showing the net long wave radiation. So this is the complete surface energy balance in one figure. And so the black is showing the cloudy skies, the green is showing the thin clouds, and the blue is showing the clear sky. And on the upper left is showing the observations. And you can see the regimes where we're getting the observations. For example, for the cloudy skies, you are primarily getting upward sensible heat flux and upward ground flux. And you can see the CAPS model is doing a good job of representing this surface energy balance But on the lower figures, these are two of the models that underestimate both the liquid and the ice. And you can see on the lower left, the HRO model actually is simulating the regimes that were observed correctly, but is not simulating their frequency of occurrence, whereas the IFS is producing variability in regimes that are completely unobserved. So this is just showing a framework that we've developed to try to understand how different processes, for example, changes in sensible heat flux may be impacting the cloud processes and vice versa. So next slide, please. So this is just to show that some of the current work that we're doing. So we're taking what we've learned from this model intercomparison, as well as our other CAF studies, and we're applying it to trying to improve the simulations of Arctic mixed phase clouds in the UFS. And so we're using a single column model. This is showing one case. So in the middle, a single layer mixed phase cloud that was observed during Mosaic. And on the right is showing simulations with a single column model using 3 different parameterization suites compared to the observations shown in black. And I just wanted to make the point here that and this is a very common thing, and Andrew showed this as well, if you get the liquid right, the ice is underestimated. If you get the ice right, the liquid is underestimated. And we think that this is because we're not really looking at this from a phenomena perspective. We're not trying to simulate adequately the cloud system itself. In the past, we've just been tuning the liquid to get the radiation right because it's such a hammer on the system. But we're really stepping back and trying to do a better job of redoing the parameterizations to get both the liquid and the ice right in the cloud. Thank you.
Excellent. Thank you very much, Amy, and thanks everybody for your introductions here. We're now going to transition to a panel discussion. I'm going to moderate this discussion. We have a series of developed questions that we'll ask of the group. I'm going to ask of the panel to just speak up. Pretend like we're in a room together and not on Zoom. Don't worry about raising hands because hopefully you'll have so much to say I won't be able to keep up with the hands. But generally, as Hazel mentioned earlier, this is a respectful space. So I hope that you do disagree, but I hope you can do it respectfully. And let's foster some good conversations here. And then for those who are on the call, as you listen and develop your own questions, please feel free to submit those to the Q&A session. If they're immediately relevant, I can kind of bring those into the discussion. If they're not, we're going to have another 15 minutes or so towards the end of the meeting for more interaction with the rest of the meeting attendees. So we do hope that you will also actively participate and formulate questions along the way. With all that, let's get started. I think the Mentimeter questions earlier on showed that many people at this meeting, at least, are still skeptical of the performance of a variety of different modeling tools and representing Arctic clouds. You saw answers that ranged from ha to so and how people thought we were doing. So I think I'll throw this question out to the panel. Are we improving our modeling capabilities when it comes to representing Arctic clouds? I assume most of you will think so, given that this is part of the jobs that you are carrying out on a daily basis, but perhaps provide a little bit of detail on where you think we've made the greatest improvements over the last 5 to 10 years or so. Nobody wants to jump in.
I'll start. I kind of alluded to my slide already. So during the short time of E3SM development from V1 to V3, we have paid much attention on cloud microphysics, aerosols into the Arctic. Our improvements are mostly in cloud phase, like Amy mentioned. The cloud ice, low bias has been a big issue for many models. So we intended to improve that aspect, at least from the cloud phase perspective.
Yeah, I want to echo on that. At GIS, there's been a lot of effort to improve the representation of mixed phase clouds, and that showed in the latest evaluation I've done, comparing the latest version of the model with the previous one, the latest version is right on spot when you compare with global observation of the satellites. And they've been doing a lot of work to implement a double moment scheme, like from Morrison and Gettelman. With what they've done, we are now able to reproduce like those super cool liquid clouds with supercool on top and precipitating ice below. And we've been comparing that also to ground-based observation using Israel Silber simulator, ground-based simulator, and everything is doing very. It's very nice to see such an improvement and being able to reproduce those very tricky clouds. That's very encouraging. And on a more global note, I want to say that I've been also working on CMIP models, trying to compare them with satellite observation. And what I've seen is that all those models that have been implementing what I like to call complex microphysics in their scheme are doing a much better job than those using a temperature ramp to reproduce mixed phase clouds. And they are very close to observation, most of them, those complex models. And those using just a temperature threshold to separate liquid and ice in climate models, they are way off, and they are actually producing far too many liquid compared to observation. Believe it or not, that's what it is. So that was my 2 cents.
Well, this is Donny from Barahona. I'd like to add something to that. I think I just want to emphasize what Long and Greg just said. Two-moment microphysics has been I don't say a game changer, but it has been a lot of progress in the modeling of Arctic clouds when you introduce two-moment microphysics that had links to the aerosol and to the liquid droplets. I think that's a very important aspect of this, and you see that in the literature. Moments, what Greg just mentioned, complex microphysics, two-moment and up, but I haven't seen anything that is up from two-moment. That's a lot better than single-moment microphysics. And the problem, however, is that a lot of the forecasting systems, they don't include two-moment microphysics. They actually they are still running single-moment schemes.
I would just like to say that we have to look at this from a multi-variable perspective. We can't just tweak the aerosols. We have to develop a framework to look at about how all these processes are interacting.
Thanks, Amy.
Go
ahead, Don.
No, I was just going to emphasize that yes, I agree with that, but the connection to the aerosol is essential.
So, Lisa, I wonder if you have any thoughts on this. I think some of the things that are being discussed are probably relevant and less relevant to the model that you're representing. So I wonder if you want to speak up at all.
Yeah, thanks. I think we have also made a lot of progress within the UFS. We have switched recently from the GFDL cloud microphysics to the Thomson microphysics, there's two-moment. The challenges that we have is the UFS, like I said, it can be configured into a global or a regional application. And for the global, the GFS and GEFS, we are not running the aerosol-aware version of Thomson, so we cannot fully take advantage of the double moment to the extent that we would like yet. And the challenge there is about global representation of aerosol is challenging. In the Rufus configuration, we have the aerosol-aware version, but we also had some challenges with aerosol, essentially just lumping it into ice water friendly and liquid water friendly aerosols. And I think our ultimate goal would be to have prognostic go-kart aerosol fully coupled together with our microphysics scheme. We're just not there yet. So those are some challenges that we are facing, is the kind of global data set of aerosol that would work well in the Arctic, I think doesn't exist.
Thank you, Lisa. On this topic of aerosols, I think it's a really important one. And I was a little bit surprised that during the Mentimeter question on what we needed to do better, that aerosols didn't rank higher on the list. I wonder if people have perspectives on the role that the particles play and the extent to which we trust that our future aerosol, particularly in the forward-looking kind of climate models, are representative of what things will look like at that point, and what sort of impact that might have on our simulation of clouds. I see How Long's smiling, so I'm guessing he has some thoughts, but I hope this is a good conversation starter for the group.
Yeah, anyone? Andrew, please.
Yeah, I'll comment on that. I think, I mean, coming from a perspective where we spent a long time worrying about aerosol models in some of the more complex Earth system models, the aerosol representations, I think, have advanced, but the interaction of those aerosols with the microphysics, and that includes sort of the budgeting, the scavenging, and the evolution, I think, is really problematic, particularly in the Arctic, because we're relying on transport. It's not local emissions. So the concept of just getting an aerosol data set for the Arctic to apply to a forecast model, I think, is going to be very tricky, because it's this interaction with what happens to the aerosols when they get in the cloud, how do they get scavenged, and how does that evolve? And so I think it's not, my personal bias is that the aerosol microphysics in a lot of these models isn't killing us. It's the aerosol coupling with the cloud physics and the rest of the models, and the evolution and transport. And that's an area where we've advanced the aerosols and we've advanced the microphysics, but as I tried to give everybody a flavor of, I think it's the connections between them that are really where we can make advancements now, and the consistency between those.
So Andrew, on that topic, I mean, do you think that if we look ahead 20 years, right, and we have an open ocean surface in the Arctic and dust everywhere from the surface, are our models going to do that correctly?
No, not yet. And there's a variety of things that we have to get right. I mean, we have to understand the surface emissions, but you have to understand the transport. And then with particular regard to the cloud physics, it's once you get an ice nuclei, how does it get processed and where does it go? Does it get out of the atmosphere? Does it stay in the atmosphere? Is it, is there sublimation? And that will govern, in the remote Arctic, what the aerosol populations look like and what's actually there. Is it transport from above? I showed the Southern Ocean example where there was potentially new particle formation or crustal material coming into a cloud layer from the top. So I think understanding, putting those pieces together, and I think some of the data sets like Mosaic are going to help us in that regard. But that's harder to do, say, from some of the satellite data, even some of the active sensors, to see that in those concentrations.
Yeah, I just want to comment on that. And I think you just, in the end, you said that it's difficult with the observation we have currently on a global scale. And they want to tune down the AOS mission, so we'll be able to do even less. And that's a shame. That's a shame. They removed the HSRL. So we won't be able to look at those interactions between aerosols and clouds. That's a shame. Yeah,
that's been an ongoing battle for the last year, is trying to get to make sure we continue those observations that Tristan was talking about and that Greg was just talking about.
Okay, my question on this is how close do we actually have to get on the aerosol concentrations? I mean, if we're getting within, say, a factor of 2, are we doing okay? But one of the problems with the Arctic, in some ways, it's the worst place, because you can get errors by multiple orders of magnitude because you've got such a range of conditions. You've got highly polluted and extremely pristine conditions otherwise. So how close do we have to get?
I think in terms of climatology, yeah, could be off by 2-3 orders of magnitude. For event-based, if you're talking about if the model is a concentrated transport like fire plume, or that could be even larger. So that's the problem.
So one other topic that came up during the Mentimeter questions was representation of the surface. And I wonder, Jad, do you have any thoughts about, related to your studies, how well we're representing the surface and what sort of impact that has on our ability to get the clouds right?
Yeah, because I focused on the sea ice lead or openings specifically, so I might be biased a little bit here. But when Andrew Gittimer was talking about the coupling of the microphysics to other systems in the Arctic, for example. Yeah, I feel like this is really one of my questions as well, because I did some sensitivity tests and to really see in the Arctic clouds, the clouds simulated in GFDL-CM4 is really sensitive to this very small increase of the turbulent fluxes that are over the openings, especially in the wintertime. So I guess my question is like, even if we have a perfect, more than or much better microphysical schemes in the cold atmosphere that can better represent the Arctic clouds, I'm not quite sure whether we can capture those sensitivity of these microphysical schemes to other forcing, for example, the surface forcing from the CS need. So back to, I guess, to Kai's question, I think for my representative, the surface fluxes, especially in the wintertime, is quite important or quite central for the Arctic, especially those low-lying Arctic clouds that are really just right above the surface. And we see a lot of these clouds, mostly mixed phase clouds in GFDL-CM4. Not quite sure if this is the same case in other modeling centers, but this could be something we can think about.
Thank you, Xia. Other thoughts on the importance of the surface? How about our observing network? I think a couple times observations have come up. We talked about observations of aerosol, for example. I think the broad question I'll throw out there is, what do we need to observe that we're not, or what are we observing but not well enough, or do we have all the observations we need? Multiple choice for the group.
Oftentimes what observations we often have are at the surface, but it's big question as to whether the vertical profile is very different than what you see at the surface.
Yeah, that's a good point, Keith. I think that's something that comes up frequently and something that groups have been working towards helping to address, either from spaceborne sensors or airborne sensors. Other thoughts?
I mean, the Arctic obviously is a unique environment, and I think it's very interesting. We've basically only talked about active sensors from space because the passive ones we've pretty much given up on. There's not really contrast in any wavelength, either the visible for half the year or the IR or anything that we typically use. So we've gone to the active sensors, which also gives us the vertical resolution that we need, and then we combine that with the surface. I think the surface measurements are critical. The longer term records are critical. The sort of things like the SGP site and Mosaic are also very valuable. I think we sort of taken those measurements and learn from them, and then we have more to do. There's complexity with the surface sites, except for Mosaic, because they're often at boundaries. If you put something on a coastline, as many of you know, it gets really tricky to work with that data to figure out, is that representative of the Arctic, and how representative of the open ocean that we're worried about for climate is it really? Or the open ice. So that interface is important, but it's also very challenging. So I don't think we have all the information that we need. I think we've made a lot of progress. I mean, as we've seen, the active sensors are phenomenal for giving us cloud phase. And that's been a real game changer for having accurate long-term measurements of what that looks like in the Arctic. It's basically identified the problems, and it's allowed us to try to approach getting the wrong answer for the right reasons in the model. Instead of just trying to match the radiative fluxes, we can now match the radiative fluxes, plus we understand it has to do with cloud phase. And now we're going down the chain of how do we get the cloud phase right? How do we interact that? And that gets your question, Heis, of are we going to get it to change properly? Will it evolve over time as the surface changes and as these sources of aerosol change in the Arctic? We're not quite there yet, but I think that's sort of the chain that we're going down.
Well, if I can add something. So yes, it has been a game changer, but we're still missing quantitative accuracy in cloud phase observations, especially from space. we know that the LiDAR and radar tend to saturate pretty quickly. So the ice water path or ice water content that we can, or liquid water content we can get from those, it has a lot of uncertainty. So we can get ice liquid partitioning at least qualitatively well, but then to actually evaluate our models, it would be nice to have something that is more quantitative, and that is still missing, at least from my
but
point.
that's where I think the ground-based observations or the aircraft, the in situ observations, we've been able to get some of the quantitative values of ice and liquid from those measurements. So I think that's a very good point.
I'd like to save a little bit of time for group discussion, but I will throw one other topic over the fence here because I think it tends to get a reaction. And I wonder what this group of panelists think about all of the recent discussion on secondary ice production and its importance in getting our Arctic clouds correct. There's a lot of work going in this direction. I think there are a lot of uncertainties and unknowns about how to get all of those numbers to match up correctly. So I'd like to just hold the group a little bit and see if anyone has input into how we can best tackle this question of the mismatch between measured INPs and the ice that we measure in the clouds. And it's okay to be controversial and say it doesn't matter at all.
It probably depends very much on what model or what existing ice nucleation schemes you're using. I guess like the heterogeneous ice nucleation now consider mostly dust as INP, and even the parameter different relationships and also other species. If you have enough dust in the model, you probably don't need that secondary ice. But if you don't, that could, when you compare to observations, it's good to compensate, right? But I think within climate models, it's hard to determine whether those mechanisms are correct. It's definitely need more process model and observation to verify, and then put in a climate model to see if actually improve.
I'm gonna say something. Well, this is from well, it seems that it's a consensus in the ice community that secondary ice production is one of the main things that we need to know over the next 10 years to improve our models, besides ice nucleation, of course, or at least on the part of with ice nucleation. And the thing is that it seems to be that to be much more widespread than we thought, and also that there are more mechanisms that originally were the people originally formulated. So far, there are at least 8 identified mechanisms for secondary ice production, and they seem to be active at very high, very low temperatures, -20, -25. So that could be quite important. And one thing is that once secondary ice production sets on, then your primary ice production really doesn't matter, because the multiplication is several orders of magnitude, and that tends to forget initial conditions. And there is well, many people in the community saying that, well, that means that we don't really know how to model number concentration just yet. So yeah, there is a push to, well, not a push, but there is some consensus that secondary ice production is a very important process, and we need to, if it is important at the smaller scale, we need to find a way to represent that also in the Corsair models and in the GCMs. So yeah, I would say that is very important, at least for, from my point of view.
Thank you, Donovan. Any other comments on this? Otherwise, maybe we'll move to some of the questions submitted by the group. The first of these comes from Lauren Zamora, who was asking whether people had opinions on what type of key information could potentially be derived from additional aircraft campaigns.
Well, I think we mentioned a little bit of that. I think getting quantitative estimates of some of these, of mass for liquid and condensate, so we understand the relative importance of that. And then getting at the liquid and ice number concentrations is another critical one to understand those environments. I also think the turbulence is important because we can get that from aircraft in a way that we can't get it from some of the satellite measurements to understand how that coupling works. So if you just see generally liquid or ice, but you have a sequence of sort of, turbulent eddies that are creating variations in that, that's something that an aircraft is much better at looking, or ground base is much better at looking at than trying to get at from space.
Thanks, Andrew. Other comments or questions on that particular topic? All right, well, maybe we'll move on. Matt Shoup asked a fairly open-ended question, which is what are the biggest current limitations for further progress? And he cites some examples, including ice nucleation, secondary ice production, subgrid scale processes, aerosol budgets, etc. What do people see as the biggest obstacles to overcome in the next few years?
Yes, Matt.
Yeah, I think the obstacles are different, and if you are trying to model the cloud, depending on the scale of the modeling, LES has a different scope than global models, and I think it would be nice to have like this multi-scale modeling projects where we can take whatever is developed on the LES and then try to use that to parameterize the global models. And yeah, those three things are probably what I would consider the most important ones.
Amy, I wonder if you have any thoughts on that, based on your range of experience with a range of different modeling types.
Yeah, I mean, I've just been thinking, listening to the conversation and thinking about how the issues with the aerosols and the ice nucleation has really masked the problem with the turbulence, and what kind of approaches can be used to look at both somehow, because I think we've had such issues with getting the IMP right and the activation right of ice that we haven't really been able to focus on the issue with the turbulence, which I think is fundamental.
Absolutely.
Yeah, that's a good point.
It's interesting that certainly I was working on some measurements, including turbulence. If you use machine learning to tell you what is more important, turbulence is actually not on the top list. It's interesting because AI knows that model always does bad, so they can systematically correct that.
Well, so I think the turbulence and it has to do a lot with the aerosol transport. If we want to get the ice nucleation right, we need to get the aerosol right, and the aerosol right needs to have it's coupled. It's decoupled from the surface. Where is it coming from? Those things are, and those are incredibly difficult to model, right? In a GCM. I mean, this is how do we even parameterize that? And it's I think the help has to come from higher resolution modeling like LES and other things.
There's one last question from Wisla Maslowski, and it's more of an open-ended opportunity for comment, I guess. And specifically, Wisla is wondering about ways to reduce model biases for liquid and ice clouds at the same time. And I think we've seen a little bit of information on that during the panel today, but I wonder if people have thoughts about how whether that's sustainable and likely to continue moving forward, or whether we've kind of been able to optimize our liquid ice balance in these modeling tools that we have. Is that a yes, Hailong? Yes, we've optimized it, and it's about as balanced as it can get.
Yeah, I had to comment on every question, but
please do.
So we normally tune the partitioning to get to reduce either bias in liquid or ice, But if the total is not correct, determined by the amount of moisture, heat, or then the resulted temperature and humidity not correct, then there's no way your physics can capture liquid or ice. So in that sense, physics are still secondary to those, the ambient conditions that the model can simulate.
Yeah, I'll second that. I mean, we of course, because of the nature of what we do, we are focused on microphysics, but yeah, the larger environment plays just as an important role as microphysics and aerosols. I was saying, to mention something else about microphysics, it's ironic that we don't have a good understanding of CCN activation at low temperature, at very low temperature. And that CCN research is a lot older than ice nucleation research. Well, not older, but it has been a lot more developed. And yeah, it's still very uncertain how temperature affects CCN activation, and that having some work on that would be awesome.
We did have one other question come in just at the end here, which is from an anonymous participant, but that anonymous participant asks or mentions that cryosphere researchers in particular hope that improved cloud microphysics will result in improved Arctic precipitation modeling. Would improved precipitation observations or more precipitation observations help us to constrain model cloud microphysics in a way to help reduce uncertainty in the precipitation processes, and particularly do things like identify when snowfall might be excessive?
I'm not sure about the answer on the modeling side. I just want to say that I feel that there's a lot of uncertainty regarding precipitation from space, and this wasn't really emphasized in the presentation, but there is a lot. And there's a paper from Israel Silber showing that when you look on the ground base and you compare that with satellite observation, you're missing a lot of light precipitation from space. And so that's something to consider. And I feel like, yes, we need a lot more observation on precipitation. And for that, we would need a better radar in space, more sensitive. And this is not what's going to happen, unfortunately. So we'll have to rely on ground-based observation a lot more.
Great. Well, we're running out of time here. We have 2 minutes left, and I'm going to pass it back to Wilbert to close out the meeting. So Wilbert, or maybe Richard, I don't know, but you guys can decide who would most like to do that. So thanks everybody for this great discussion.
Go ahead, Wilbert.
No, please do the honors, Richard. Thank you.
Well, I'd like to thank very much everyone who participated today. We did ask a broad group of the Arctic Cloud community to join this presentation. Many people had other things to do, and it's a busy time of year. So I thank very much everyone for giving their time for this meeting. And I think we had some really great presentations and some great discussions. So thanks very much for that. So we'll be thinking about ways forward from here. Perhaps we might contemplate a white paper. I'm not sure. We can discuss that in the future, but that is something that we can think about. But for the moment, I'd again like to thank everyone. Wilbert, do you have anything to add?
No, I don't. It was a wonderful session. I really appreciate the contributions from all the panelists, and especially from the presenters. It's very insightful, even for a physical oceanographer like myself. So thank you very much.
Okay. Thanks very much.
Yeah, and maybe thanks Hazel for running the show and for
thank you, Hazel,
engaging and Mentimeter episodes. It was very nice.
The modeling team will have a meeting in December. We'll have more details on that. Heist, do you have anything to announce for the atmosphere team?
I don't at the moment. I have a meeting with Barry, hopefully in an hour or so, to look ahead beyond the upcoming IRPIC workshop. So atmosphere meetings will likely restart in January. I would assume at this point it's getting pretty late for a December meeting. So thanks everybody for joining, and Richard and Wilbur, thanks for inviting the atmosphere team to be part of this discussion. Hazel, thank you for your efforts, and I think it was a great meeting.
Okay. Thanks very much, everyone. Bye-bye.
Here. Bye-bye.
Thanks all.